is Mick, and please check the room because this is the tutorial on Sunday music computing. And if you're not for this tutorial, you may. Oh, it's right there. Okay, let's start. In this tutorial, I'm going to talk about the project called Virtual Percussion Set. In short, it's called VIPS. I'm going to talk about the architecture of this project, basically about how you build the project. If you guys remember that I've shown this project as the first lecture of this class. And then I'm going to briefly explain how I build the project using a software build its neural network. Okay. Go to the table of contents. First of all, I'm going to introduce you guys what kind of technology I've used in this project. We have used a smartwatch called the Gear S3, powered by Samsung. And another one is how we communicate between the Gear S3 and Raspberry Pi using a Bluetooth Low Energy technology. And then I'm going to talk about the architecture of the software and system. After that, I'm going to give a demo of how to build a neural network using the software called Neural Designer. First of all, this software is about using your hand gesture to control music playback in the Raspberry Pi, which means that we need to use some sensors in the smartwatch, right? And there are many sensors we can use in the smartwatch right now, but we only use two of them. The first one is called the linear accelerometer, right? The first one is called the linear accelerometer. It's called the linear accelerometer because it's a little bit different from the regular accelerometer. As you guys already know that the regular accelerometer is just recording the three-dimensional acceleration of the smartwatch when you move it. But you all know that because we are all on the Earth, so the acceleration of the smartwatch is affected by the fact of the Earth has its gravity. So the linear accelerometer is by doing some calibration with other sensors, like magnitude sensors and gravity sensors, to exclude the data value of the gravity in the acceleration. So another sensor that we use in this project is called the gyroscope. The gyroscope is also a three-dimensional sensor, and different from the accelerometer, is just capturing the angular rate and angular velocity of your smartwatch. And these two sensors that we use in the project are all set to 200 Hz assembly rate. Because, well, in this project, we want the assembly rate as high as possible, well, in a certain range, but, well, we want it as high as possible. And then we have tested that if you set it higher than 200 Hz, it's going to lose some accuracy. So we just stick it to 200 Hz and it's working okay. And the next one is the communication between the smartwatch and the Raspberry Pi. We use a wireless technology of communication called the Bluetooth Low Energy. It is introduced by the Bluetooth 4.0. As its name suggests, Bluetooth Low Energy, it uses less of the energy and is faster to set it up. Well, according to the documentary of the Bluetooth company, it is set it up only use 5 or 6 milliseconds, but actually the reality is not. But anyway, we're using it, and this is the architecture of it. It's called the gate architecture. Basically, in a Bluetooth Low Energy architecture, we call every Bluetooth devices the peripheral. In this project, the peripheral is the Gear Galaxy S3. In every peripheral, we're going to have several services, or you can have non-services at all. In each service, we can have several characteristics. The characteristic is the object in this architecture we mainly deal with. The characteristic will show what kind of things or tasks this service or this peripheral can achieve. For example, it can tell the user, well, this service can be read, or it can be written, or it can send notification to all the other devices it's connected to. And it also can store some information inside. For example, you can store a screen inside. You can store a number, a digit inside, whatever you want. And this is the brief introduction of the technology that we use in the project. After this, we are going to move to the architecture of the project. as you may already know before, this project consists of 3 parts. The system consists of 3 parts. The first one, well, is the Galaxy Gear S3. It's a smartwatch powered by Samsung and is running a Tizen application we built it on it. We're going to talk about later, and then the information the Gear S3 application provided will be sent to Raspberry Pi using a Bluetooth Low Energy communication. And the Raspberry Pi is going to play sounds based on the received messages through a speaker right here. And the Raspberry Pi is powered by a remote power supply. Now I'm just using a power bank. Okay, let's move to the Raspberry Pi. In the Raspberry Pi, we are running a Python application. If you guys not familiar with Raspberry Pi, it's just a single chip computer. As I've shown, it's like this kind of size, and it runs a Linux-based system called Raspbian, and you can run Python, whatever programming language you want on it. And it has built-in Bluetooth, has built-in NFC, has built-in Wi-Fi. So it's a quite useful IoT device that you can use in your development. And in our project, the Raspberry Pi running a Python library called the Blue Pi. The Blue Pi will connect, it will start it by scanning all the BLE devices in this area. And it will find the nearby VIPS-enabled watches, which means the watches that run our application. If it finds a VIP-enabled watches, it's going to connect it to it, and then listening to the notification that's sent by the watch, which means the result of this gesture recognition. And apart from the Raspberry Pi application, this shifting overlapping window is the one that we use in our smartwatch application. As we all know, that if we are dealing with sensors, we need to have a window. Window means, well, in this period of time, in this maybe fixed period of time, or maybe shifting period of time, we are receiving the sensor reading from the sensors. And in this situation, we're using a shifting overlapping window. And what you can see is a little bit different from the regular window that we're using in other applications. Well, there are 2 reasons for that. The first one is, imagine a situation when you are reading sensors reading in a regular window. Imagine there are 20 samples for each window, and the gesture takes about 20 samples. And what if the gesture happens in the 10th sample? And it will end it at the 30th sample, which means the first window takes the half of the gesture, the second window takes another half of the gesture, which means we lose some information through this kind of deviation. So this is causing some misclassification, so we don't want to use that. Another reason that we're not using the normal window is because, it causes latency from it. For example, the similar kinds of situation that we have here. 20 samples per window, and what if the gesture only takes about 5 samples? And what if the gesture is happening at the very first sample? And then, after the gesture ended, there are another 15 samples in that window, and we have to wait till the end of that window to process this gesture, which gives us about, 100 milliseconds of latency. That's the thing that we don't want in this project. So we're using a shift overlapping window. For this one, we can see that after it started, in each sample, we start a new window, and it's overlapping with each other. And in this project, we have 20 samples for each window, but in this figure, we only have 10 samples for each window. It's just because 20 samples is too long. But you guys get the idea. And at end of each sample, we're going to perform the data segmentation and gesture recognition after the data segmentation, which are basically in the same session. Okay. You may ask, when we are using this kind of overlapping window, a problem may appear, which is, because we have overlapping, whatever gesture happens right here, and it's here. And this window will recognize this is a gesture. And this window also say, this is a gesture. this is a gesture, this is a gesture, this is a gesture. Well, this window doesn't know it at all, so it doesn't know this is a gesture. So we can have multiple output when we are using the overlapping window. So to solve this problem, it's very easy. You can think about it. It's just at the very end of each gesture, we have a counter to say that, well, this gesture is being classified by the last window or not? Is it classified by the last window? If it is not, then it appeared right here. And if this gesture ended in the, let's say, this window, it's just saying that, well, this window also classified this one as a gesture, but the next window doesn't classify as a gesture. Then we know that gesture is ended, and the period of the gesture is within this period. If you guys understand that. Okay, so let's move to the next part. Okay. The feature scouting, I don't know if you guys have heard it before. Maybe you guys know it in another name. It's called data normalization. The data normalization in maybe every machine learning methods and neural network building is just very important for you guys, for the modeling. It's because, well, your data set are all real numbers. It comes from the real life. You gather it by your sensor or other devices. So it happens when your data is heavily distributed to one end, but the other end is loose distributed. So when it happens, when this kind of situation happens, we find it out that neural network or the machine learning will focusing on the heavily distributed section and losing interest in the loose distributed section. We will lose some information by the data set. So we don't want that kind of situation to happen. So we need a feature scouting. The feature scouting, which is also the data normalization. It put all the data in one data set in a fixed range, which using this kind of formula right here. If you guys don't want to know it, it doesn't matter, because the output is only -1 and 1. So we put every value in one data set in the range of -1 to 1. And that's something that we want to do. And it will probably, remember, it's probably increasing the accuracy of your model. So because sometimes it doesn't, but sometimes it does. So because we are building a model, we want it to be optimized. So we just do it all the time. And this is one of the method. It's called the minimum and maximum scouting method. The formula is input minus minimum and over the maximum value and minus minimum value. You can see that it takes the scale input into, the position inside the dataset between maximum value and the minimum value. Well, in this method, we will lose some information. For example, the distribution information of the dataset. Because all the data in your dataset are related to each other. What if this group of dataset is heavily distributed to the far end and loose distributed to the other end? When this happens, this method will lose some information. Well, it has more information than if you're not doing the feature scouting at all. But to overcome this kind of problem, we have another one. This one. This one will be, I don't know, maybe more familiar to you guys, because this one is actually just called data normalization. It's using the standard deviation instead of the maximum value and minimum value. It's very straightforward because it considers the deviation to be one of the factors of your data set. Okay? And a little bit different because this scouting method will output the value from 0 to 1. Sorry? Okay.
Can you go back to the last slide, please?
Okay.
So the minimum and maximum, are those the minimum and maximum of all possible inputs?
Yeah.
Because what?
Not all possible inputs. The maximum and minimum is, you have a data set already.
Yeah.
You have a data set already. Let's say you have like 100 instances in your data set. And they are all different. They have all different values. And the maximum is those values.
Because then wouldn't that mean that the scale inputs would only fall between 0 and 1?
Sorry, I don't really get it.
No, it's just because I was wondering how you could get a negative value for the scale of input if the input is always greater than or equal than the minimum.
Oh. Oh yeah.
Yes, should be between 0 and 1.
Yeah. Yeah, maybe that's okay. Sorry for that.
Yeah.
Sorry for that. Okay. Okay. Yeah, you're correct. I'm very sorry that I have some problem with that. Okay, so the idea, you guys get it. And well, let's continue to the next part. The next part is I'm going to introduce about the neural network model that we have in this VIPS project. First of all, I'm going to introduce guys about the data set I have. In this data set, we have 3150 gesture instance inside. And we recorded from 4 people. Each person has 14 gestures, which I'm going to introduce the 14 gestures to you guys later. And for each gesture, we have 50 instances. So 4 people, 14 gesture, and 50 instances for each gesture is about 3,000. And we have more than that, so it's like 3150. And when we were recording the data, we want the record environment is, well, as similar as the one that we deploy in the model. It's because you will increase the accuracy when you deploying the model inside your application. So we're using the same model of smartwatch, same application, same sensor configuration, which means the 200 Hz one. And when we're recording the data, we implement a threshold method. The threshold method in this recording data session, we set it to be a very low value because we want to capture the gesture from the very beginning of the gesture. So this will cause another problem. Sometimes it just misclassified of, well, this is a gesture, but actually this is just a sneeze of the participant or something. So when this happens, I mark when there's a bad reading there and exclude it in the dataset because we don't want a bad reading inside our dataset. And then the data collection session will take approximately 40 minutes. So maybe if you guys choosing to do the similar project in this lecture, then in this course, then maybe you can take this as a reference. Okay. After we collect all the data, we want to build a neural network model. In the lecture, introduction to the neural network model, introduction to the machine learning methods, we have learned that well, the neural network model takes the input layer, hidden neuron, and output layer. Instead of introduce you guys how to do it in coding in Python, I'm just going to give you guys a software called Neural Designer. It's a very simple software and it has several very useful tasks, several useful functions. It takes a CSV file as input and it can perform several tasks. For example, it can select what kind of input and order it have in this neural network. And it can do training, testing, validating by automatically. It can have scaling method choosing, training method, hidden layer number, and hidden neural number. If you want to use PCA in your model, it also has a supporting for PCA. And most importantly, it has a reporting one. When your model doesn't perform so well, this application tells you why it is not so well. And maybe you can choose based on the reporting. Okay. And in our model, we have using a scaling method called mean standard deviation, which is the data normalization one. And we have 1 hidden layer, 8 hidden neuron inside this layer. And the data set is, as the one that I mentioned before, it's 60% of training data, 20% of validation, and 20% for testing. This is the example of what kind of gesture we use in this neural network model. We designed 14 gestures. Each gesture, well, initially we only have 7 gestures, going up, use your hand, going down, use your hand, going left, use your hand, right, go forward, go backwards. But when we test on it, we find it out if you just use one hand to record all the data, or it appears sometimes if you use your left hand to do one gesture, it may be misclassified into another one. We don't want that kind of situation to happen because we can support several smartwatches at the same time. So we divided one gesture into two, using your left hand, using your right hand. This is the first 7 of it. And for each gesture, we give it a code, which is the one that we use in the neural network. We're going to expand it later. We can see the first one is a up gesture using your right hand. And the code is 13-0 followed by a 1. That means this is the first gesture. And the second one is the last second digit of the code is 1. That means this is the second gesture. Others are the similar things. And another 7 gestures, all the similar thing. And the last one is the idle one. Idle one means you use your hand right here, basically doing nothing. In a slow way, you're not doing anything intentionally. This is the input that we have in this neural network. We have 38 variables as the example shows here. We have 24 in the very first is the input variable, are the input variables. And the last 14 are the target variables. The target variables are basically here, the code of each gesture. In this example, you can see that the very last digit of the target variable is 1, which means this is the first gesture using your right hand going up. And then, this is the workflow of the neural designer of the neural designer application. As you can see, you can choose to use what kind of scaling method, what kind of PCA, and the training method, model selection, and you can perform training in one button, and reporting. And very importantly, this application allows you to output the neural network result using Python or R. And then I'm going to give you a demo of how to do it. Before that, I'm going to introduce you guys an issue or a problem in machine learning on the internet. It's very famous. I think you guys have heard it before. It's called iris flower classification. No? Okay. So basically, iris is a kind of flower, but it has many braids inside. We want to classify what kind of braids of the flower is. So in this data set, we take 3 types of the flower. I'm not going to pronounce their name because they are in Italian. Flower 1, flower 2, and flower 3. And as you can see on the picture, they're very similar because they are all iris flowers. And the difference between these 3 kind of flower are only the difference in the length of the sepal and the length of petal, or something else. I'm not going to translate here. So to classify these 3 kind of flowers, we take 4 input variables here. The first one, they are the length and width of the sepal, the length of the width of the petal. This is one example of the instance inside the dataset. You can find this dataset very easily on the internet. You just type in the iris flower classification problem, and there are a lot of datasets right there. This is one of them. To put it as an instance in the neural designer, we just put it in this way. Because we have 3 kinds of flowers, so we just put it 0, 0, 1, because this is the first kind of flower. And in this data set, we have 150 instances for 3 kinds of flowers, and 50 instances for each flower. These are the examples of the data set. From left to right, the first one is flower 1, flower type 2, type 2, type 2, type 3, and type 3. Straightforward. And I'm going to demo you guys about how you do it in Neural Designer. we firstly have a CSV file. The CSV file contains the 150 dataset inside, which this is it. 150 instance inside and all modeled for the input. And open the application, the Neural Designer. This is the UI of the Neural Designer. Here, you click on, you have a new classification project. And we want to put it inside this folder. I'm just going to call it 14 Fed Iris. Okay. And inside this interface, we want to input our data file. We find that CSV file that I just showed you guys, click on it, and it shows what kind of instance inside. And they separate by comma. Done? And they automatically just input this file inside. We can see the data set inside. We have 7 variables, and the variables are looking like this. Because we know that the last 3 variables of these 7 variables are the target variable, so we want to mark it here as a target variable. Okay, before I move further, I have to tell you guys, in this project, if you choose to do the using a smartphone or a smartwatch to control your music playback group project, you don't have to use a neural network to do your gesture recognition. And you don't have to use this software to do your neural network. I'm introducing it right here because it's very simple to use. It's very easy for beginner. But sometimes it doesn't do a really good work. But most of the time, it just finish the work properly. If you want to explore the very professional way of building a neural network model, we recommend you to use TensorFlow or other professional tools. Okay? After we mark it as these last 3 digits are the target variables, very easily, there's a button here called Perform Training. Amazingly, we can just do that. We input that CSV file, we do nothing, and perform training. And after that, it performs train very well. As I mentioned before, there is a report function inside. Sorry. What if here we set report confusion? So it automatically separated the validation set, the testing set, and the training set for you. And here it takes 30% of the data, 30 instance as the testing set, which is the 20% of the data set. For the 30 set, we have 8 for the flower 1, 11 for the flower 2, and 11 for the flower 3. You can see here, it has 100% accuracy, which basically because, well, our data set is very simple and easy to classify because it's a very well-known problem. Here I'm going to show you how to, because there are many factors or configurations you can do when you're building a neural network model. For example, what kind of method you are using, and how many input layer and neural network hidden neurons are there. I have to say that there are many factors that affect your output when you're choosing one kind of method. And these factors could be, well, the size of your data set, well, the distribution of your data set, and maybe the value inside your data set. There are many factors. And I'm not going to deep talk about it here. I'm just going to say what I did for choosing all these things is test them all and compare the results to find out the best one for your project. Which is another benefit of this software, is it tests it for you. Here, we can see that it chooses the scaling method to be the mean standard deviation as its method, and it chooses the number of layers to be 2, 1 hidden layer and 1 output layer. In the hidden layer, it has 3 hidden neurons. It also used the Queisson-Newton method as the training method. It is all automatic and it's very easy to use. Another thing that I want to talk about this software is it can perform a input selection. That means some of your input may not be so important to perform a classification. And when you do the input selection, remember that we have 4 inputs for this model. And here, after input selection, it turns out there are only 2 of them are, I won't say crucial, most importantly for you to classify this kind of problem. And after we perform the input selection in the dataset, we can see that there are 2 inputs are unused. And if we calculate the confusion matrix, we can see there are only 1 missed classification for the flower 2. So, basically this software is just very easy for you to use it as a beginner. And that's all for my presentation today. Thank you.
Yes.
Yep.
I want to know how you know if the future is important.
Oh, in this software, I guess it's using the PCA for testing if the input is important. And I don't really know the detail of this software because, well, it's a commercial product. And using PCA is just my guessing. Okay. If there's no other questions, I think there's another talk, right?
Yes.